Welcome to the end of the movie. So let's wrap up Calculus 1 with section 5.6, Substitution and Area Between Curves. So we've done the U substitution stuff before. We did it in the setting of indefinite integrals though, so we're going to transition into applying U substitution techniques to definite integrals. And we'll also define area between curves in terms of an integral, and we'll evaluate find some areas bounded by curves by using definite integrals and oftentimes a U substitution. So you've got one technique of integration in its U substitution. We just haven't used it in definite integrals yet, and we're about to. And the theorem that introduces the U substitution to definite integrals simply has to deal with the bounds. It says, if G prime is continuous on the interval AB and F is continuous on the range of G of X, it's called G of XU, then we can write the integral from A to B of F of G of X, G prime of X, dx, as an integral with a lower bound of G of A, an upper bound of G of B, F of U du, where the U represents the G of X function. So all we've done is change variables. We changed the variables, the X variables into U variables, and we had to change the bounds because this one's a definite integral. Maybe a little observation here. There's a lot of talk of continuity. G prime is continuous, F is continuous where it needs to be. Right? I don't see F of X, I see F of G of X. That's the reason for the wording about continuity on the range of G of X. We have a continuous integrand is what those hypotheses give. Well, when you got a continuous integrand, the function which you're integrating, fundamental theorem of calculus applies. So that's the reason we have those hypotheses. Let's look at a proof of this substitution in definite integrals theorem. We evaluate definite integrals using antiderivatives according to the fundamental theorem of calculus, part 2. So we need to be thinking antiderivatives. Let capital F be an antiderivative of lowercase f, standard uses of those symbols. Then consider the derivative of capital F of G of X. Composition of functions. Remember, U substitution is really just the chain rule backwards. So let's look at the chain rule forwards to motivate the proof. Differentiate this composition. We'll differentiate the outer function, the capital F function. So we'll get capital F prime, rewrite the inner function, lowercase g of x, times the derivative of that inner function, which is g prime of x. Chain rule right there. Told you we're using the chain rule backwards. And by the way, if capital F is an antiderivative of lowercase f, then capital F prime is lowercase. That's what it means to be an antiderivative. Differentiated, and you get the function f itself back. So we can replace capital F prime with lowercase f, and then this produces lowercase f of g of x, g prime of x, rings a bell. That's the integrand on the left. So we found something that we can differentiate to get the integrand. In other words, that something, capital F of g of x, is an antiderivative of the integrand. Well, we evaluate definite integrals using antiderivatives. So the definite integral of f of g of x, g prime of x can be computed using an antiderivative, any antiderivative. Well, here's one right here. Capital F of g of x, we'll evaluate that from A to B. We found an antiderivative. We're taking the antiderivative and evaluating it at the bounds as told to do by the fundamental theorem of calculus, part 2. Substitute in the A and B, we get f of g of B minus capital F of g of A. That's capital F of u evaluated from a lower bound of g of A to an upper bound g of B. Can't argue with that. I just did some change of variables. We've let u equal g of x. So this would be u equals g of b. This would be u equals g of a, where I take u to be the variable inside the function capital F. All right, there's a change of variable stuff, by the way. And that produces, then here's where we left off, that produces the same as an integral of g of a, an integral from g of a to g of b of f of u du, where we've got u equal to g of x. How would you evaluate such an integral? Using an antiderivative. Well, you got an antiderivative right there. So again, this is the fundamental theorem of calculus, part 2, that connects together these two things. And that's what was claimed. This integral equals this thing here. So what we've done is we've taken a rather cluttered integrand and made a clever substitution to change it into something, in a sense, more elementary. And you know how this goes from your experience in the past with indefinite integrals. There'll be a u part and there'll be a du part when we actually go to doing the computations. All this says is you're dealing with these integrals the same way you did when you were dealing with indefinite integrals, and you're adjusting the bounds, since these are definite integrals, as appropriate in that substitution. So back to the notes. We can use U substitution in definite integrals simply to rewrite things like this with a substitution u equals g of x, and as we did in the previous section with the indefinite integrals, we'd compute the differential du, and that would be g prime of x dx. So this becomes g of u, this becomes u as before, and then I need to find the u value that corresponds to x equals a. That'd be u equals g of a. That's why that's the lower bound. And I'd need to find the upper bound of u that corresponds to b. When x is b, u is g of b. And that's why we get the upper and lower bounds in the new integral as stated. Of course, the big idea is to take something sort of complicated and write it as something a bit more elementary. Notice, as we've seen in U substitution before, this doesn't evaluate the integral, it simply changes the form of the integral. It makes it more elementary. And if you're lucky, you can find an antiderivative of this f function. We dealt with it symbolically in the proof. Computationally, you'll have to find antiderivatives. So let's look at a couple of examples. Evaluate this definite integral. Okay, we've got some stuff to the -1/2 power, some other stuff over here. As you know, I rather expect the u to be in a composition, like that first term is. Also, whatever we let u equal, we'll need to find the derivative of u, or a multiple of the derivative of u floating around somewhere. I bet you the derivative of this first part is some multiple of this. Okay, so let's try to let u equal g of y be, g of y and the symbols introduced above, y cubed plus 6y squared minus 12y plus 9, this stuff here. Then the derivative, g prime, is 3y squared plus 12y minus 12. Is that this? No, it is not. But I can factor a 3 out of this. Then it gives us 3, y squared plus 4y minus 4. Hey, there it is, y squared plus 4y minus 4. That's there. Aren't we lucky? Of course, it's a set up to work by U substitution. So it's a literally textbook example. Quick comment about hypotheses. I'll mention this in the beginning a few times, and then we'll just work forward and not do quite this level of detail. But f is continuous where it needs to be. Yeah, it's polynomial, so it's continuous everywhere. G prime, also polynomial. These things are continuous, continuous everywhere. So theorem 5.7 does apply. Excuse me, it required a continuous integrand, and we got a continuous integrand. Okay. Let's see, continuous everywhere. Yeah, I got little concerns actually about that square root thing. we're dealing with this, I guess, where we have continuity. 0 to 1, I need continuity there, and I trust this never produces negatives between 0 and 1. So we could explore that in more detail, but we do have continuity as needed on the interval 0, 1. Maybe I went overboard here by saying everywhere. Possibly I could get some negatives down here, and that would cause us some trouble. But between 0 and 1, we're good. A is 0, B is 1. Let's evaluate G of A and G of B, G of 0 and G of 1. Crunch the numbers, and we get 9 and 4 respectively. Okay, this looks a little odd. We're going to have the 9 is the lower bound and the 4 is the upper bound. Usually the lesser number is the lower bound and the greater number is the upper bound, but not with a substitution. So we'll take the given integral, rewrite it in terms of U's following Theorem 5.7. So on the next page, we'll have an integral from G of A, that's 9, integral up to G of B, which is 4. The f function is the -1/2 function. I don't think we stated that just yet. And U will be as defined here. Okay, so here's what we had on the previous slide. We're then dealing with this becoming something somewhat different. We needed to have the 3 times this over here for the G prime. Let's go back and look at that. I want to see G prime to match things up. Like I said, we're going to do this one a little bit different. We'll streamline these here shortly, but I want to see G prime sitting right here on the right. And G prime going back, G prime was 3 times what's sitting there. Okay, I'll put a 3 there. Of course, I got to divide by 3 somewhere else to keep things equal. So we're putting a 3 there and dividing by 3 at the same time. Okay, then this is exactly f of u, g prime of u, d, dy in this case. I can make the substitution. Then we get an integral from, we saw the lower bound was going to be 9 and the upper bound is 4, which looks a little weird. The 1/3 came from the manipulations we did. U is raised to the -1/2 power. Du is exactly this stuff here. This is g prime of y dy. So actually we're substituting into this formula if you like. Integrate, okay, u to the -1/2, add 1 to the exponent, gives us u to the +1/2, divide by 1/2, that is multiply by 2, produces this. Plug in the 4, plug in the 9, do the arithmetic. It simplifies, I guess, to -2/3. So let's not belabor the point on the arithmetic because we got other things to do. But there's our first example of U substitution in a definite integral. Let's do another one. Okay, how about this one? Evaluate the integral from pi to 3 pi halves. Cotangent to the 5th, theta over 6, secant squared, theta over 6. Well, we're used to seeing secants and tangents together in this stuff. So let's change it so we've got secants and tangents. Or we've also seen cosecants and cotangents together before. So I got a couple of choices here. I could either take this cotangent and write it as a 1 over tangent, or take this secant, well, secant squared, and write it in terms of cosecants. We get 1 over cosecant. Is that right? That's not right. So we get 1 over cosine. Let's take the cotangent and write it in terms of tangents. That's how it's written up. I've got other options. I can turn everything into sines and cosines and try that. The fact that I see a secant squared here, that's the derivative of what? Tangent. That's fairly suggestive that I want to use this stuff as the du part. But we can't have cotangents and secants together, so something's got to change. Let's take the fact that cotangent is 1 over tangent and rewrite the cotangent to the 5th as a 1 over tangent to the 5th of the same argument, that theta over 6. Then we'll have secant squareds and tangents together. The derivative of tangent is secant squared. I'm thinking we should let u equal tangent. Well, theta over 6, the 6 will have an impact as well. Okay, so we can see the integrand then as secant squared, theta over 6, over tangent to the 5th, theta over 6. Let's take u to be tangent theta over 6. I kind of think about that first. What's done to u? It's in the denominator and raised to the 5th power. So the f function in the symbols of theorem 5.7, f of u is 1 over u to the 5th, because we have 1 over tangent to the 5th, theta over 6. And we'll need the derivative of g prime of theta, with g of theta is tangent, theta over 6, derivative tangent is secant squared, theta over 6, chain rule spits out a 1/6. Not calculating differentials in this notation, though I do rather prefer the notation where we do calculate differentials, still using the notation of theorem 5.7. But here's what we get for g prime. We've got continuity. Yeah, I know I've definitely gone overboard. I don't know about everywhere, but we've got continuity where we need it between pi and 3 pi halves. So hypotheses of theorem 5.7 are satisfied. We've got a equals the lower bound of pi, b equals the upper bound of 3 pi halves. We need to take those a's and b's and turn them into u's. Here's how you translate thetas into u's. So when a equals pi, we'll plug pi in here. We'll get the tangent of pi 6. So g of a, g of pi is the tangent of pi over 6. It's 1 over the square root of 3. It's 1 over the square root of 3, special angles. Plug b in, g of b over 6. That would be 3 pi halves over 6. Simplify, that's g of pi fourths. That would be the tangent of pi fourths, and tangent of pi fourths is 1, so that's a little more familiar. Now we're going to rewrite the given integral in terms of u's. So we're taking it from thetas to u's. That's the substitution. That's the u substitution. We get this formula here. All we got to do is take the a and the b and replace it with the here it is, the g of a and g of b, the 1 over the square root of 3 and the 1 we had above. We're letting u be the tangent function, so we'll get 1 over u to the 5th. There's the g prime function, except there's a 1/6 it looks like that we needed to introduce. Chain rule had given us a 1/6. We'll go ahead and put a 1/6 there. That is the g prime function. To keep the books balanced, I need a 6 out front. So a 6 and a 1/6, and this is exactly g prime of theta as we had on the previous slide, the 1/6 that came from the chain rule. So we can rewrite the integral in this form. And that's a fairly elementary integral. It's a power of the variable. It's an integral of u to the -5. Add 1 to the exponent, divide by that exponent, plug in the bounds, plug in the upper bound of 1, the lower bound of 1 over the square root of 3. Deal with the arithmetic. The square root disappears. This is deal with a negative exponent to take a reciprocal. And then we get the square root of 3 to the 4th power. That's what? 9. Square root of 3 times square root of 3 is 3. You're going to do that twice. So it's 3 times 3. Yeah, that's 9 that we get out of that. And the arithmetic simplifies down so that this is 12. So there it is, evaluated by matching up with theorem 5.7. Let's do it without such direct appeal to theorem 5.7. Let's do the u substitution in the differentials thing. So we're shifting gears here. Same problem, really the same computations, but a kind of streamlined notation. Okay, so here's what we started with. We had rewritten it like this. Let's let u equal tangent theta over 6, just like before. Then du is secant squared theta over 6 times 1/6 divided by 6. d theta, almost like before. The only difference is before this was g prime of theta, and now it's a differential du. I prefer this. It's a more of a streamlined way to deal with it, and you see things kind of balance a little better. When we deal with it like this. We had to stick a 1/6 in before. That'll be taken care of with the differentials here in just a second. In fact, let's cross multiply here. Take the 6 to the other side. We'll get 6 du is secant squared theta over 6 d theta. Okay, do you see a secant squared theta over 6 d theta up there? Sure do. That's why we got this 1/6 out of the way. So I see that up there. So this secant squared d theta stuff will be 6 times du. There's u in the denominator. So we can turn all of these thetas into u's. Oh, don't forget the bounds. They got to be changed from thetas to u's as well. As we saw in the previous slide, plugging in pi produced 1 over the square root of 3. Plugging in 3 pi halves to the g function produced 1. And that's the bounds we'll have correspondingly as before. We were integrating the 1 over u to the 5th function. Let's write it as u to the negative 5th. And then anti-differentiate. Looks like I've dropped a 6 here. Where'd my 6 go? I should have a 6 out front. Another little typo. Should have a 6 out front, as well as a 6 here. There it is. It mysteriously reappears over here. But yeah, I dropped a 6. Making the substitution for this numerator. Yeah, we get a 6du. So yeah, I dropped a 6 there and there. I'll edit that in the notes. And we do the arithmetic and we get 12 again. So I got away with it by getting the correct answer. But I have dropped a couple of 6s there. And I like this way better. I don't have to do the G prime stuff and artificially squeeze 1/6 in there. It all comes out in the wash. It comes out in the wash from the fact that we've dealt with differentials and moved some things around until we've matched the integrand and the d theta part. So there's a couple ways to work those. The second way I prefer without such a direct appeal to that substitution and definite integrals theorem. A little application is now given to even and odd functions. We talked about even and odd functions probably in chapter 1. So let's recall what an even and an odd function was. Function f is even if f of negative x equals f of x. So whatever it does at x, it does the same thing at negative x. The graphs of even functions are symmetric with respect to the y-axis. So I know you've encountered this idea before. And we're requiring this to hold for all x's in the domain of the function. A function's odd if f of negative x is negative f of x. The reasons these are called even and odd is, for example, x squared functions, those absorb negative signs. X to the 4th functions absorb negative signs. X squared plus x to the 4th absorbs negative signs. Cosine functions absorb negative signs as well. So cosine functions are also even. Examples of odd functions are x cubed. They spit out negative signs. X to the 5th spits out negative signs in this sense. Sine function spits out the negative sign. An odd function in general is symmetric with respect to the origin. If you've dealt with these symmetries in your past, say in pre-calculus. Well, it turns out if we integrate even or odd functions over symmetric intervals, the symmetric interval is one of the form negative a to a. So left and right endpoints differ by a multiple of -1. If we integrate, and this makes sense if you'll think of it in terms of the symmetries, but we'll go through the calculus and establish it. If f is continuous on the symmetric interval from negative a to a, if f is even, the integral from negative a to a of f of x is twice the integral from 0 to a of f of x dx. Yeah, it's symmetric with respect to the x-axis. So whatever it does to the right of the, symmetric with respect to the y-axis, whatever it does to the right of the y-axis where x is positive, it does a mirror image thing when x is negative. So the integral from negative a to 0 is the same as the integral from 0 to a by the symmetry. And we'll see that happen when we compute this. If f is odd, then the integral from negative a to a of f of x dx is 0. Ooh, that's because whatever it does for the positive x values, it does the negative of that for the negative x values. That's what the definition of an odd function is. And those integrals from negative a to 0 and the integral from 0 to a, in this case, they cancel out. In this case, they double. In this case, they cancel out. It's based on the symmetries. Let's look at the proof. Okay. First, before we do either of those, let's note by the additivity property, The integral from negative a to a can be written as an integral from negative a to 0 plus an integral from 0 to a of f of x. So first we'll split it up like that, and notice the right-hand side of the first one deals with this. The left-hand side is also going to deal with this and this, it turns out. Okay, for even functions, we have f of negative x is the same as f of x. Even functions absorb negative signs. So if we were to evaluate the integral from negative a to 0, f of x dx, this part, by the way, I call this equation star, so we'll refer back to this a couple times. If we look at the integral from negative a to 0 of f of x dx, where f is an even function and absorbs negative signs, let's make a substitution. Let's let u equal negative x. All right, then negative u equals x, so the x becomes a negative u. Du then is negative dx, so the dx becomes a negative du, right? I'm liking the differential notation, and I have to change the bounds as well. When x is negative a, as it is over here, the corresponding u value is negative a, or a itself. When x is 0, u is negative 0. So this becomes an integral from a to 0, f of negative u du. Okay, let's pick that up on the next slide. Here's where we left off. All right, I can bring this negative sign out front because that's how integrals behave. What's up with this? F of negative u. F's an even function. It ignores the negative. It absorbs the negative. So this negative sign disappears because we have an even function. This negative sign comes out front as a negative. So we've produced this. Let's have an integral from 0 to a, and that's what the other side looks like. So let's use the order of integration, which says when you reverse the orders in which you integrate, you introduce a second negative sign in this case. So introduce a negative sign in addition to this one, they cancel, and the order gets reversed. Reverse the order of integration, introduce a negative sign. All right, so that'll give us this. Variables or x's or u's or whatever they're called, dummy variables. So let's get rid of this dummy variable u and write things in terms of x only. So the integral from negative a to 0 of f of x dx equals the integral from 0 to a of f of x dx. Simply change the u's into x's. Of course, the bounds don't have to be changed then. Hey, that's what we get on the right-hand side. So when we had by asterisk or star that the integral from negative a to a was the integral for the left-hand half plus the right-hand half, well, they're the same size. So I can substitute for this integral, and we get 2 copies of this. And that's what was claimed. Yeah, it doubles up. Doubles up when you have even functions integrated over symmetric intervals. Okay, let's deal with odd functions. It'll be basically the same, but somewhere in there we'll pick up an extra negative sign and we'll get cancellation down here. Let's do that. If f is an odd function, then f of negative x equals negative f of x. Definition of an odd function. Okay, so let's try the same stuff. We'll get started the same way. Integral from negative a to 0 of f of x dx. Let's let u equal negative x. Same computations we had before. Bounds are as given. This negative sign comes out front, say, f of negative u, that'd be negative f of u. Negative signs come out of odd functions. So this negative sign comes out of that function. That didn't happen before the negative sign disappeared. So this is where we're picking up an extra negative sign. I can cancel these 2 negative signs, and that produces an integral from a to 0 of f of u du. Let's reverse the order of integration, just like before. That gives us an integral from 0 to a with a negative sign thrown in. So the sign change comes from reversing the order of integration there, producing this. And let's write it in terms of x, because who cares what the variable is? Let's use x's instead of u's for that dummy variable. All right, now if we'll go back to the start equation, we had the integral written as the sum of these 2. We just saw that the left-hand one, the integral from negative a to 0, is negative integral from 0 to a. So substitute that in for the first one. We've got negative this quantity plus this quantity. They canceled out this time and you get 0. Kind of think of it as, well, the one on the left was negative and the one on the right was positive. Of course, that's not what odd means. It could be the other way around. And there was some kind of symmetry to it. So we get these things to add together to give 0, and that's what we claimed. Let's do an example. Really just another example of integration. Also with secants and tangents in it. I like having secants and tangents together. It's got a secant squared over here, and there's a tangent. I bet you we let u equal tangent. So du will be secant squared. And there'll be some 1/2 or something floating around, but we'll keep the books balanced. Okay. Integral from negative pi halves to 0, you're asked first. In fact, this is suggestive that maybe we can do some doubling up on this second one. It's not an even function nor an odd function, so we can't. We have to deal with these separately. Integral from negative pi halves to 0. Tell you what, let's let u equal tangent, because the derivative of tangent is secant squared. U is tangent t over 2. So we have no control over the argument, the t over 2 part, we're stuck with that. And then du, derivative of tangent is secant squared, so we'll get secant squared t over 2. The chain rule will insert a 1/2, right? I didn't draw the little arrow and the square brackets and all of that, because we're near the end and maturing in this procedure. You pick up a 1/2, and it's a chain rule that puts it there. So we get du equals this. Let's get the 2 out of the way and move it to the other side. Is 2 du equals secant squared t over 2 dt. There's the secant squared t over 2 dt. This is the du part, the du stuff, and this is u. So we can take this integrand and entirely convert it from t's into u's. Don't forget the bounds. They got to be changed from t values into u values as well. All right. So when t equals negative pi halves, u equals what? Here's the formula for u. It's a tangent of t over 2. So we'll have the tangent of negative pi halves over 2. That's the tangent of negative pi fourths. That's -1. I recommend you pause this video and think about these little computations. They're correct. Tangents of pi fourths or negative pi fourths, those are easy to compute. 0, when t equals 0, the upper bound, then u equals a tangent of 0 over 2. Tangent of 0 is 0. So the new bounds will be a lower bound of -1 and an upper bound of 0. So we'll take, we left off here, we'll take this. No, sorry, we left off here. We'll take this and entirely convert it into u's. 2 plus u. This was what? 2 du. 2 du over there. So everything is accounted for in the integrand. The bounds change correspondingly. Lower bound corresponded to -1 as a u value. Upper bound corresponded to 0 as a u value. So we consider this integral here. So the substitution is done. We've technically we've used theorem 5.7 there, so let's not get into that so much hands-on. But don't forget to change the bounds. It'd be the easiest way to mess these up. You've changed variables. You've changed everything in the integrand. You've even got rid of the dt and changed it into a du. Don't forget the bounds. They have to change as well. So we need to integrate this. Let's take the 2 and distribute it to get 4 plus 2u. Anti-differentiate that using the fundamental theorem of calculus part 2 right here. Antiderivative would be 4u plus u squared, right? Introduce a u, 2 u squared over 2 if you like. So you skip some of the anti-differentiation steps if they're very elementary. Evaluate from -1 to 0, plug that upper bound in, plug that lower bound in, take a difference. Be careful with parentheses. It'd be easy to drop a negative sign in this stuff, and we get out a value of 3. Okay, so there's the first one. Second one, it's going to be very similar because it's got the same integrand. We'll make the same u substitution. We'll have the same du stuff going on. The only thing will be different is, looks like the upper bound is changed from 0 to pi halves. Okay, so that'll change a little part right here. All right, for the second one, they wanted an integral of the same integrand, but this time from negative pi halves to pi halves. All right, making the same substitution, same differential, same cross multiplication by that 2. Same lower bound substitution to produce -1. Upper bound, here's the new part, really. T equals pi has for the upper bound. It's not 0 this time, it's pi has. Plug that into the formula for u. U equals tangent t over 2. Fine. When t is pi halves, u is tangent pi halves over 2. Tangent of pi fourths is 1. We'll get that as a new upper bound. So it becomes an integral from -1 to 1. Converted it into u's, distribute the 2, find an antiderivative, plug the 1's and the -1's in, and this time we get 8. Okay, so there's what we get in terms of this definite integral, changing the bounds. Like to see tangents and secants together. When I see tangents, I got my eyes out for a secant squared. I guess my alternative perspective is when I see a secant, I'm looking for secant tangents, maybe the derivative of secant. I might see one of those, but I don't think I see enough of them. Back to the notes. Okay, so now we're going to shift gears a little bit and talk about areas between curves. Note 5.6.a, I'd only give it a name if I'm going to refer to it later. Consider an area above a function y equals f of x and below the function y equals g of x. For x between a and b. All right, so I got my aboves and belows backwards from what my picture is. We'll take upper function minus lower function. I've misstated this. I want f of x at the top and g of x at the bottom. I should interchange the above and below, and I've computed it as given by the picture. So, excuse me, upper function is f of x, lower function is g of x. We want to find this little blue shaded region given here. Okay, we're going to make an argument that, similar to how we did this when we first developed integration a few sections ago, I'm going to take the interval from a to b and cut it into a bunch of little pieces. Partition the interval a to b. That'll introduce rectangles. We'll choose x values to determine heights of those rectangles, and then we'll add them up. That'll give an approximation. Then we'll take a limit, and that'll produce a definite integral. So this simply describes that. Partition the interval a to b up. We've got bases of little rectangles of size x sub k minus x sub k minus 1. We'll choose some c sub k somehow or other in this interval, and we'll use that to determine heights of the rectangles. Since, this is why my little typo really matters, the f function is the upper function and the g function is the lower function. When I take an f of x value minus a g of x value, that will be positive. So we really are integrating a positive function or non-negative function. So we'll get positives out of this because we will get things which are integrals of non-negative functions. And in that case, totally an area representation, none of this quote unquote area stuff or signed areas. Okay, so we'll do the area approximation. It'll be the changes in the functions times the base, the delta x sub k, as stated here. The total area is approximately the sum of those little areas of rectangles. That'd be a sum of f of input value minus g of input value times the delta x. That's a Riemann sum. If we vary the partitions in such a way that the norm of the partition approaches 0, the actual area should be a limit as the norm of the partition approaches 0 of these Riemann sums. And that is a definite integral. So there's a fairly formal argument that the area between those two curves should be the integral from a to b of f of x minus d of x. F of x is the upper curve, g of x is the lower curve. We get the integral of the difference of those two curves, upper minus lower, and that determines the area. Formally, we'll actually define the area between the curves f of x and g of x, where f of x is greater than or equal to g of x. and x ranges from a to b, we'll define it to be that definite integral. All right, so now this is how we'll find areas between curves. You will do loads of applications of definite integrals in Calculus 2 at the beginning of Chapter 6. Chapter 6 really picks the ball up where we've left it off here. I think it's a little bit later that you'll get more techniques of integrals. That's kind of good news. It means for now, all these applications you'll do of integrals to find volumes and work and all sorts of stuff, they'll only require U substitution to evaluate the integrals. So U substitution is fairly powerful stuff. So let's find some areas between curves in a few examples. Okay, number 58 from the section, they give us the picture. They won't always do that, but let's start with one where they give us the picture. We want an upper function and a lower function. Let's call the upper function f of x equals x squared. Let's call the lower function negative 2x to the fourth, I guess, the blue function. So f is the red function, g is the blue function. The f function's on top, the g function's on the bottom. The area they're interested in is between -1 and 1. I see some obvious symmetries here. We could take advantage of that. I think both of these are even functions, symmetric with respect to the y-axis. I bet you we could find the area of this right-hand part and double it. It has that kind of symmetry. Let's not exactly go there in Calculus 1. You might want to do some of that if you do a lot of these things, like you will in Calculus 2. So we've got exactly what we were just describing and defining. We're looking for an area bounded by f of x and g of x, above by f of x, below by g of x, and the x ranges from -1 to 1. That's an integral. That's a definite integral from a to b of f of x minus g of x. Here, a is -1, b is 1, so that sets up the bounds. There's the function difference right there. Let's clean it up a little bit, and that's an easy integral to evaluate. To the second page, we got it set up as an integral. Okay, here's where we left off. Anti-differentiate, 1/3 x cubed. Anti-differentiate, add 1 to the exponent, we'll divide by 5. We'll get 2x to the 5th over 5. Plug in the 1, plug in the -1. One thing I like about this prepackaged stuff, I know it goes by awfully fast, but do the arithmetic, all the details are spelled out there. And we'll get 22 over 15. Is that a reasonable answer? What's that, about 1.5? About 1.5. It's positive. If it ain't positive, something's wrong because it's an area, and areas are never negative. Does the size of it make any sense? We don't often check that. Let's try. It may not work very well. See, it's 2 units from here to here. Got 1 unit from here to here, 2 units from here to here. You know, I got to draw a big box around it, and that'd give me an upper bound on the area. That I can reliably do. This big box that would encompass this would be 3 units tall and 2 units wide. So it'd have an area of 6. Did we get something less than 6? Yeah, we got, what was it, 22 over 15. What we've done is not obviously wrong. In fact, I got high confidence in it, but it's a good idea when you've got a picture and you can check the answer, check it to see if it's obviously wrong. If I got out like 7, that's wrong. I know it can't be bigger than 6 because I can box it in with something that has area 6. The fact that it's exactly 22 over 15, well, all I can really do is trace through the work and double check all the work. But I can check for obvious mistakes. The most obvious one would be it's an area, better not be negative. The size of it, I can't always tell. And this time I couldn't tell with much accuracy. But this isn't obviously wrong. That's a good thing to check. Good thing to know. The details, I just have to track through and double check all the computations. But I think this one's right. Let's do another one. Okay, same kind of question, except they didn't give you a picture this time. Maybe there is a picture in the book. This is an example from the book. So as a worked example, they do give a picture. Find the area of the region in the first quadrant that is bounded above by the square root function and bounded below by the x-axis and the line y equals x minus 2. good thing they gave us a picture. So here's what they're getting at. So we will have to generate our own pictures here before it's over with. Here's what they want. So it's bounded above by that square root function. It's bounded below by the x-axis here and bounded below by the line y equals x minus 2 over here. Okay, we'll just break it into two pieces and represent those pieces as definite integrals. They've actually given it away in their picture, but let's have a more detailed conversation about that. For x between 0 and 2, the region's bounded above by the square root function and bounded below by the function, if you like, y equals 0, the x-axis. For x between 2 and 4, the function's bounded above, still by the square root function, but it's got a new lower bound. It's bounded below by y equals x minus 2. All right, so we could write this part of the area as an integral from lower function 0 up to upper function, upper minus lower, square root of x minus 0 on this one. And that would be good from 0 to 2. For this one, upper minus lower, square root of x minus 2. And that's valid from 2 to 4. Let's explain it in more detail if they plop the answers out in their little figure. But we'll write it as an integral from 0 to 2, upper function minus lower function. Upper function was a square root function, lower function was the x-axis, y equals 0. Let's write all that stuff out. 2 to 4, same idea, upper function was a square root function. This time the lower function was x minus 2. So we'll subtract x minus 2, be careful with parentheses. Let's clean that up a little bit. This is simply a square root of x. Let's write it as x to the 1/2 because we're going to need to anti-differentiate it. Let's distribute that negative sign, and that produces this. And this is exactly what they had in their picture. Maybe they used the square root radical instead of the 1/2 exponent, but that's what they had in the picture. It's upper minus lower over the appropriate intervals. So this will be the area of the left-hand chunk, and this will be the area of the right-hand chunk. We'll simply add them together. I need antiderivatives. Antiderivative of x to the 1/2, add 1 to the exponent, get x to the 3/2, divide by 3/2, that is multiply by 2/3. Differentiate it, that's correct. Evaluate that from 0 to 2. Antiderivative of this, there's an x to the 1/2 again, same antiderivative. Negative x, I'll need negative 1/2 x squared and 1 to the exponent, divide by 2. So 2 gets introduced there. 2, an antiderivative is 2x, and evaluate that from 2 to 4. Plug in the 2's and the 0's, only one term here. Plug in the 4's and the 2. Plug in the 4, produces this stuff. Always put things I substitute in parentheses. Plug in the 2, produces this stuff, and take a difference. Right? We took a difference of plugging in upper bound and plugging in lower bound. Here we're plugging in upper bound minus plugging in lower bound. So inconvenient place for an end of line, but it's exact same type of computation. Don't forget parentheses because there's a good chance you could drop negatives on this stuff. Crunch through the arithmetic, it looks like we get 10/3. You want to check that for accuracy. What is it, 3 1/3? Man, let's take a look at that. It's positive. First off, it's computed procedurally pretty much the same way we did the others. Let's go back and look at the picture. But we had to break it into two pieces because of the upper function minus lower function deal. It was what, 10/3, 3 1/3. Does that make sense? See, this is 4 units wide, 2 units tall. It should be less than 8. Well, 3 1/3 is less than 8. How much less than 8, I'm not so sure about. Let's see, 2 units wide. We got 1 unit right here. Gee, I don't know. I could analyze this, I suppose, more guessy. But we got a positive estimate of the area, and it's less than a big box that encloses the whole thing. So it's not obviously wrong. Could still be off. The only way I could check the details of it is to double check all this arithmetic. But again, it's a good idea to check for obvious things that have gone wrong. So let's do another one. What can complicate things is when I don't always have the same function on the top and the same function on the bottom. like here. This is exercise 5.62. They give us a picture. Sometimes the red function's a top function. Sometimes the blue function's a top function. So, well, we'll have to integrate. They cross at 0. They cross at 0. Then we'll have to have an integral from -2 to 0, upper function minus lower function, plus an integral from 0 to 2, where they intersect again, upper function minus lower function. But the uppers and lowers swap at 0. Okay, so let's call f of x the red function. It's the upper function here. And let's call the blue function g of x. The red function is greater than or equal to the blue function for -2 to 0. And then they swap. Then the g function, the blue function, is greater than or equal to the red function, the f function, for x between 0 and 2. So they swapped. All right, well, then we'll just write the area as an integral of red minus blue, f minus g, the way I've labeled them, for -2 to 0. And then this part must be the integral of the blue one minus the red one, the g function minus the f function, over the interval from 0 to 2. Reading off those x values to get the bounds on the integrals. Okay. That produces these two integrals. Upper minus lower from -2 to 0, upper minus lower, 0 to 2. Okay, upper and lower different from one integral to the next. Yeah, it's because the functions crossed at 0. Let's simplify. So we've got a difference, simplify it, simplify this one as well. They should be related by a negative sign, right? And they are, so we're doing the arithmetic probably right. Anti-differentiate, okay. Anti-differentiate, okay. Those should differ by a negative sign as well. You want to simplify those. I got 8 over 2. We can write that as a 4. 2 over 4 we can write as a 1/2. So let's simplify it. So we've done those simplifications here. Plug in the upper and lower bounds, producing these things here. Here's where we're adding the two together. This first part produces, looks like, let's see, 8 minus 16 would be -8 with a negative sign out front. So we're producing an area, it looks like, of 8 from both of them. So there's not exactly a symmetry. It looks like those areas are the same size if I partitioned it up properly here. And we get a value of 16. So it looks like we got 8 from each of those integrals. Let's look back and see if that's reasonable. I think these are the same area and they're both 8. That's plausible, right? The scale's a little bit off here. The X and Y scales aren't calibrated to the same level. Here's 2 units on the X scale, and looks like about half that on the Y scale. Yeah, they got to go down to -10. This is what, like about 12 units from top to bottom. From side to side, it's about 4 units. That'd be 48 units. I can put a box around it a size 48. Well, we got something less than that. Also, I'm not entirely sure that it's just capped at 2. Right, this is the 2 value. Looks like both of these functions may go a little bit bigger than 2. This is harder to analyze in great depth because I don't know exactly where these functions had their maxes and their mins, but we could figure it out. But it's a positive answer. It's within the realm of reasonableness. The only way to check it at a higher level of detail is to double check all the arithmetic. But there's another one. Finding areas using integrals. Only thing you got to worry about is that you don't introduce any negatives in this. I want upper function minus lower function. For that, I'm likely to need a graph. Another one. Find the area of the region enclosed by the line y equals x and the curve y equals sine pi x over 2. Number 90, they didn't give you a picture for this one, so we got to graph this stuff. No worries. I know how to graph y equals x. I know how to graph a trig function, a sine function at least. What's up with that sine function? Well, its amplitude is 1, the coefficient up here. Its period, to find the period, you take the period of the trig function, which is 2 pi. and divide it by this coefficient, pi over 2. We've got a pi over 2 coefficient of the variable. So we get 2 pi divided by pi halves. The pi's drop out, and this has a period of 4. They've done that to give you intersections that you can handle. So we get a trig function that has a period of 4, a sine function that looks something like this, between -2 and 2, has an intercept at 0, of course. And the line y equals x, these intersect at, okay. Need a little insight to realize where these intersect. Certainly they intersect at 0. By the way, they also intersect at the point 1, 1. You believe that? I plug 1 into this for x, I get y equals 1. I plug in 1 for x in the trig function, we get the sine of pi halves, which is also 1. Yeah, they intersect there. And similarly, they intersect at the point -1, -1. It's a transcendental equation to deal with this. So you need a bit of insight or a bit of luck to notice that these intersect at -1, 0, and 1. You would maybe suspect as much when you drew the graph. And this is, again, I drew this kind of by hand. I created this image in PowerPoint, not with some sort of graphing software, as you would have to do by hand. So we get these two tiny little slivers of area. I bet they're the same. I bet there's some kind of symmetry here we could explain. But on the left, the x function's on top and the trig function's underneath. On the right, the upper function is a trig function. Lower function is the function y equals x. Okay. So the upper function is the x function when x is between -1 and 0. When x is between 0 and 1, it's the other way around. So we'll write this total area as a sum of two integrals, an integral from -1 to 0 of x minus the sine function plus an integral from 0 to 1 of the sine function minus x, upper minus lower, always upper minus lower. So that produces upper minus lower, x minus trig function from -1 to 0, trig function minus x from 0 to 1. And it's just a matter of evaluating these integrals. X, easy enough to anti-differentiate, x squared over 2. Sine pi x over 2. If you like, you can do this with some U substitution. I suppose they mean you to, given it's in this section involving U substitutions. But we had a formula in table 4.2 that dealt with this. I need an antiderivative of sine. That would be negative cosine, since negative signs disappeared with the introduction of the negative cosine. And you simply divide by this coefficient. This pi over 2, divide by that to produce a 2 over pi, a 1 over k when you have sine kx is what's happened here to compare it to the table. But there's an antiderivative. Observe that it works. If you differentiate, you'll produce this original thing back. All right, plug in the upper and lower bounds and off you go. There is in fact some certain symmetries to it, and what you produce is 2 times 2 over pi minus a half. Pi is roughly 3. We've got 2/3 minus 1/2. It's what's like 1/6. It's actually a little bit less than 1/6. We've multiplied by 2. We get a little bitty area that's, I don't know, it's in the ballpark of 1/3. It's not a very big area. Does that make sense? Yeah, we got these little slivers of areas. The fact that the totality of it is 1/3 of a square unit. Yeah, I suppose that's plausible. Yeah, I'm just going to take it as I suppose that's plausible. I may not trust the shape of my curve that much because I did this by hand. It might actually be a little bit fatter than that in what I've got here, so I probably shouldn't read too much into it. I can put a box around the whole thing, 2 units tall and 2 units wide. It should be less than 4. Well, it's definitely that, and it should be positive. It passes that smell test at least. So here's what we get out when I crunch through all those numbers. So let's see. Let's go back to the notes. That was number 90. See if we can get to the end of this. last little part says, well, suppose you have x as a function of y. If we have x as a function of y, we'll do exactly the same kind of stuff, just kind of been turned sideways. How are you going to find an area that's bounded by x as a function of y on one side and x as a function of y on the other? Guess what? You're going to take larger minus lesser. The larger things appear on the right along the real number line. So you'll take right-hand edge minus left-hand edge, or right-hand function minus left-hand function. Right minus left, that'll produce something that's positive. So here we've got f of y on the right and g of y on the left, as we do in both of these pictures. The only thing that differs is they cross here, but they're looking in this area between C and D in all three cases. In this one, the curves intersect at the C and the D. Here we might be looking for the area bounded between those two functions. Nonetheless, between C and D, which is what they're illustrating here, the f function is on the right and the g function is on the left for all three of them. They touch at the endpoints, but that's where we stop the interval over which we're integrating. And all three of those can be represented as an integral of f of y minus g of y, where f is the function on the right and g is the function on the left. Let's look at number 78. Okay, find the area of the region bounded by the curves x minus y squared equals 0 and x plus 2y squared equals 3. Okay, we're going to need a graph to do this. We need to know what's on the right and what's on the left. We also need to find where the curves intersect. They wanted bounded by these curves, so that'll give us bounds over which we integrate. All right, x equals y squared, x equals y squared. That's a parabola opening rightward. X is a function of y. Let's take the x plus 2y squared equals 3 thing and rearrange it a little bit. Rearranging it, we get x equals 3 minus 2y squared. Right, take the 2y squared to the other side. That would be an opening leftward because of the negative coefficient, an opening leftward parabola. So I've drawn that one in blue and the other one in red. That right there in itself is suggestive that the picture looks something like this. How widely this one opens, it's affected by the 2 there. And how widely this one opens, it's affected by the 1 there. But this is a reasonable scale drawing. Again, I did this by hand. We need to know where they intersect. So let's set the x is equal. Let's set x equals y squared to x equals 3 minus 2y squared. In other words, we'll set y squared equal to 3 minus 2y squared. Rearrange, 3y squared equals 3. Divide the 3's out, take square root. We get y equals plus or minus 1. Obviously from this, say y equals plus or minus 1 is a solution. So these intersect when y is 1 or negative 1. You can plug those 1's and negative 1's back into either equation and you find that the corresponding x value is 1. So when x is 1, they both intersect, and they intersect at the y values of 1 up here and negative 1 down here. A little odd because we're going to have to think of x as a function of y to deal with this. So there's the region they want us to find in yellow. So we'll integrate from y equals negative 1 to y equals 1, right minus left. The blue curve is always on the right, this one. The red curve is always on the left, this one. So we'll integrate from negative 1 to 1, this minus that. Right and left, this minus that. Blue one minus red one. That produces blue one minus red one from negative 1 to 1 where they intersect. Simplify, anti-differentiate, plug in the bounds. Looks like that area is 4. So there's an integral dealt with in terms of x as a function of y. That's the same thing we did when we had y as a function of x, except up has become right and down has become left. Just think of it kind of a rotation of the xy plane. I'm still integrating things which are non-negative to get areas. So I simply need to know which is greater and which is lesser. That's why I need a picture to deal with these. Another note. All right, and then a few more examples. This note's my farewell performance here. When you deal with this integration to find volumes and other things in chapter 6, I might kind of think of little slices as little dx slices. We'll illustrate what I mean by this. This is a touch more informal. It's often called a heuristic shortcut. I think this book used to use those words. Let's introduce it now because this will be helpful for you in chapter 6 when you're off to calculus 2. So when considering areas bounded between functions, as we've done, instead of taking a partition and getting little rectangles and taking a limit as the norm of that partition goes to 0, all this stuff we did above in section 5.6a, I even didn't read the whole thing to you there. What if we just took a dx slice as opposed to a delta x slice? And instead of adding them up, let's just integrate them up. So I'm thinking of taking dx slices and integrating them up. There's a problem with that in terms of mathematical rigor, but I got some good news. It works. So what we're burying by taking dx slices instead of delta x slices and integrals instead of sums, we're getting the right answer. We're losing the math rigor. We're burying delta x's and partitions and limits. All that stuff is buried, and you end up in the right place. I'm an awfully big fan of mathematical rigor, and I'm awfully suspicious of shortcuts, but this is a shortcut that'll work. And you will use this technique so often in calculus 2. It's good to have this little heuristic shortcut. Okay. As I mentioned, what you'll do with these slices in calculus 3 is you'll do stuff to them. You'll revolve them about axes and produce something called washers or possibly something called shells. You may load them up with water and move them and do work on them. So you'll have work problems related to integrals as well. It's cleaner to have this little heuristic approach. Let's try to do a bit of illustration of that in the following and 108. So we're just going to deal with this one pretty much as we had before. We'll set it up as an integral, so we don't have to deal with the slices so much. But you'll find that heuristic stuff useful later. Find the area of the region given here. All right. We've got x as functions of y. So either we live with that or we modify it. We could maybe solve for y in terms of x. Let's leave it as it is. Probably a little bit easier to deal with x in terms of y if that's what you're given. And then I'm interested in what's on the right and what's on the left. Well, between 0 and 1, this is on the left, x equals 0, and this blue curve is on the right. It looks like these intersect there. I can check that they do intersect at the point 2, 1. So for y between 0 and 1, we get x equals 0 on the left, and x equals 2 square root of y on the right. For y between 1 and 2, we get x equals this red function is on the left, and y equals this green function on the right. So we can break it up as an integral from 0 to 1 plus an integral from 1 to 2. The left and rights change. Actually, they both change at 1, but that's okay. We just break this region into 2 pieces and deal with that. So here's the verbiage that says we've got lefts and rights as described. So we can write this sum as this area as a sum of 2 integrals. 2 integrals with respect to y, the first one from 0 to 1, second one from 1 to 2, and always right minus left. The first one, for example, will be 2 square root of y minus x equals 0. Second one will be this minus that. 2 square root of y minus 0, right minus left. This minus that, 3 minus y, minus that thing there. This minus that. Let's integrate. Let's maybe simplify first. Let's take the square root of y and write it as y to the 1/2. So we got a power of y. You know how to deal with that. Let's multiply this out. I could integrate it as is. Let's do a little algebra and save ourselves some calculus in a second. This multiplies out to, forget the negative sign for a second, that'd be y squared minus 2y plus 1. So we get with a negative sign, we get a negative y squared. We had minus 2y with a negative sign in there. That'll give us a plus 2y. We'll subtract this y from it, leaving us with a single y. We had a plus 1. The negative sign, we'll change that to a minus 1. It'll get together with this 3 to leave us with 2. So simplify. That produces this integrand. Anti-differentiate. We're using the fundamental theorem of calculus part 2. Add 1 to the exponent and divide. We've done this several times with the 1/2 to the 3/2 and the 2/3 stuff. We'll evaluate from 0 to 1. So no U substitution necessary in this one. So that's nice. They're pushing the idea of left and rights in this one, obviously. Integral from 1 to 2, we need an antiderivative. Okay, you got a square, so that'll produce a cube over 3. We got a first power, that'll produce a square over 2. Constant introduces the y. And evaluate over the appropriate values. All right, here's where we left off. Stick in the 1 and the 0, take a difference. Stick in the 2, the upper bound, and the 1, and take a difference. One last time, be very careful about parentheses and negative signs. Simplify the arithmetic, and we get 5/2. 2.5, it looks like we get out of this one. It's positive. Yeah, I could draw a box around it and see if that's a reasonable answer. That box would be what? 2 units tall and 2 units wide. Be an area of 4. Yeah, 2.5 is less than 4. So we're ballpark. It even looks like it's probably a reasonably appropriate estimate. But write it as 2 integrals with respect to y, because they gave us functions of y. If you're sufficiently stubborn, you could break this up and find y in terms of x and do an upper minus lower. I don't think you're going to enjoy it quite as much. You're going to be off to the races solving for x in terms of y. Solving for y in terms of x. Not too bad in the first one, and the middle one, that top one, I don't know, some square root stuff's going to pop up there. Well, we did have square root stuff here. Let's do it the way it was given, as x in terms of y. If you're insistent on y in terms of x, yeah, you could, you've got the knowledge, algebra and calculus wise, I think, to work it that way too. Number 114, a little theory example. It's an application of U substitution, and it's actually fairly straightforward. You're asked to show the integral from 0 to 1 of f of x is the same as the integral from 0 to 1 of f of 1 minus x. Okay. Let's relate those somehow with a U substitution. So let's take this one on the right, integral from 0 to 1 f of 1 minus x dx. And I want to let u be this thing inside. I want to see a f of something, right? And I'm going to try to change that something into what we've got on the other side of the equation. So I'm kind of stuck letting u equal 1 minus x, in which case du will be negative dx. So computed with differentials. Take the negative to the other side. If you like, dx itself becomes a negative du. So the 1 minus x, that's become a u. Dx has become a negative du. Got to change the bounds as well. When x is 0, 1 minus x, 1 minus 0 is 1. When x is 1, u is 0. So corresponding to the lower bound 0 is a new lower bound in terms of u, of 1. Upper bound of 1 in terms of x becomes an upper bound of 0 in terms of u. So the substitutions have been made. We get this. Let's bring that negative sign out front from the negative du. Let's change the order of integration. So write as an integral from 0 to 1. If you do that, you got to introduce another negative sign. 2 negatives will produce a positive. So this becomes positive integral from 0 to 1 of f of u du. And how about we use x's instead of u's? So simply calling u a dummy variable and replacing it with x. And that produces this, and lo and behold, that is the other side of the equation. So we took the right-hand side and showed it equals the left-hand side. And what we used was what we know about integration, in particular the U substitution stuff. Okay, one more theory question, also fairly easy one. It's one slide. You're asked to show in number 118 the integral from x to xy of 1 over t dt equals the integral from 1 to y of 1 over t dt. Okay, so that's kind of similar to the previous one. I'm going to make these things look alike with the appropriate U substitution. So let's start with the left-hand side this time, integral from x to xy of 1 over t dt. Okay, I want it to look like this. So I want the upper bound to be a single variable. So I'm trying to do a U substitution where I get this upper bound as a single variable. Let's let u equal t over x. Let's try that. Then I was worried about that upper bound. When t equals xy, u equals xy over x, the x's cancel, and we get a single variable up top. So the motivation on this substitution is to make this look like that. I want a single variable up there, not a product of them. Okay, we'll divide the x out, and that'll do it. There's probably a way to do this by letting u equal t over y as well. But let's write it up in terms of this. The lower bound, yeah, the lower bound might cause me some trouble then. T over y, yeah, potentially. This one works. Make that substitution. That's equivalent to saying cross multiply t equals u times x. Differentiate, then we would get du is 1 over x dt. Du is 1 over x dt. We could cross multiply there to get x times du equals dt. Right, we're trying to change from t's into u's. X's, are they a concern? You know, not this time. They're part of the integrand. There's some constants. I just don't know what they are. The variables are t, and we're changing over to variables u. X's and y's, they're just numbers. I don't know what numbers they are, but they're just fixed numbers is the implication. So let's take the integral, the 1 over t. Let's see, t is u times x when I cross multiply. So 1 over t would become 1 over u times x. And the dt stuff is equal to x du. So x du, that replaces dt. T itself is replaced by u times x. So we pick a u times x up there. Use this relationship for the lower bound, t equals x. Substitute that in there. That produces a 1 for the lower bound in the new integral, which is very good news because look what we're trying to get. When I make the substitution of t equals x times y, here, as we saw, that produces a single variable, produces y. Over here is an upper bound, also very good news, what we've got here. So making these u substitutions produces this. I really like the bounds. I'm about to really like the integrand. The x's cancel. They're just numbers. X's cancel. You're told they're positive, by the way, so there's no division by 0 going on here, which I'd worry about when I do cancellation as well, losing information. Dropping the x over x produces an integral from 1 to y of 1 over u du. Why, that is the right-hand side, except it's in terms of u's instead of t's. Make the substitution, t equals u. Now, dummy variables, think of it as a dummy variable. I'm just swapping all the u's for t's. That produces this, and that's exactly what we wanted. So the integral here and the integral there, they're the same. Another illustration of U substitution. And that's calculus 1. I wish I'd have put a little bit more in there about the dx slices. We don't need it in calculus 1, but you will find this useful in calculus 2. I've got some calculus 2 notes online. I don't have videos or anything like that, not yet. Thank you for your support throughout this calculus 1 adventure. my hat's off to you for sitting there if you've watched all of this stuff. So this was a bunch of my time too in preparing these videos. But that's Calculus 1. What you do in Calculus 2 is pick right up where we've left off. You'll use U substitution in integrals, and you'll do applications of integrals. We had to kind of briefly make a synopsis. This started with limits. When we hit the calculus material, we used limits to define and find derivatives and establish properties of derivatives. Then we did applications of derivatives. Now we've got this new thing where we're doing integrals. Not surprisingly, next comes applications of integrals. So it's been limits and limits applied to produce derivatives, applications of derivatives, integrals. And by the way, the integrals were defined using limits as well. So I told you limits is fundamental. And then the limits, the integral stuff, we've established a handful of rules. What's next is applications using the integrals. And what will follow that is you're going to try to get better at integration. So then you can do more applications of it, it turns out. But thank you for your support. Good luck in your future academic endeavors. After this stuff, you're ready for Calculus 2. Have a nice day. Bye-bye.